Welcome to the second video for SLO11. In this conversation, we'll be talking about how we would alkylate amines. And what I mean by that is taking maybe a primary amine where we have some kind of an R group, could be a methyl or an isopropyl, maybe even a benzene ring, so this could be an aniline, for instance. And we want to add an alkyl group. So we would go from a primary to a secondary amine, for instance. Or maybe we started with a secondary amine and we wanted to make a tertiary amine. So basically we're adding our new R groups. And how would we do this? Well, the most direct way to do it would be like an SN2 reaction. Or we could take some kind of, I'll show an example with a primary amine to start. So we'll choose something simple, ethylamine. And we know that the nitrogen is nucleophilic. We talked about that in the first video of the series. So it might be sufficient simply to add some kind of an alkyl halide. So maybe we could use methyl iodide. So we know in this case that our nitrogen is nucleophilic and our carbon is electrophilic for SN2. And so in principle, we could do the reaction you learned about last semester. Just a transfer of the methyl group onto the amine. And if I follow my arrows, then what I'll find is that I'm going to actually make an ammonium ion. So this lone pair on nitrogen is being used to form a new bond to carbon. But both of the hydrogens are still there. So I have a structure that looks like this. Okay, well this looks good so far. I'm getting closer to where I need to go, but you'll see that if I'm going from a primary to a secondary amine, I'm keeping the nitrogen neutral, and in this reaction I haven't done that. So we need to think about how we would remove one of these protons. But as it turns out, the pKa for this substance would be around 10. This is an ammonium ion, so we'll say pKa about 10. So it's kind of acidic, right? That means that we should be able to use some kind of a base to remove one of these hydrogen atoms. Here's the problem. This compound here is a nucleophile, but it's also a base. And that means that as the reaction goes, a few molecules initially of this compound act as a nucleophile, but there's a lot left that haven't done anything yet. And so you end up with a situation where this compound can actually react with another copy of this compound. So if we show that, we would transfer a proton from the product of alkylation to the starting material, right? So remember that as these reactions go, most of the time, starting materials are present along with products. So the products can react with the reactants. We've seen this multiple times this semester. And so when this actually happens, we now have an acid-base equilibrium where, well, let me keep everything in the exact same positions. We have made the product we want. So this is now our secondary amine. We've added an alkyl group. And we've also got the conjugate acid of this compound. So 3 hydrogens on the nitrogen, positive charge. Okay, so let's look at what we've done here. We've taken a molecule like this that we wanted to alkylate using a nucleophilic nitrogen, and we've made the nitrogen no longer nucleophilic because we've lost the lone pair. And we've taken our secondary amine and we've made it nucleophilic because we've restored the lone pair by deprotonating this compound. So, well, we've done this alkylation, we've done this acid-base reaction. Now these compounds are present, they're forming, and they're in the flask with more of our electrophile. So this secondary amine can now act as a nucleophile. In the exact same way that we did initially, so another SN2 reaction. And we end up with a tertiary amine, or the conjugate acid of a tertiary amine. Okay, so this is a tertiary ammonium ion. And then this could go on to make more products, right? You could do the same process. You could deprotonate this compound with another copy of this, or maybe a copy of this. Maybe you add a fourth methyl or alkyl group to the nitrogen and make what's called a quaternary salt. All of these products form. So you get some of this, you get some of this, and you get some other products as well. So this amine alkylation isn't very useful for us because we can't control it. So over-alkylation is a problem. Sometimes you can get away with using secondary amines to tertiary amines via SN2. This last alkylation, where we would actually take our tertiary amine and add a fourth R group, that's much slower than any of these other SN2 reactions because there's a lot more steric hindrance around the nitrogen here than there is here. We talked about that in the last video. So SN2 isn't really going to be a good idea here. You really don't want to try that. Over-alkylation is going to be a problem. SN2 could work here, but you're kind of rolling the dice. So that means we need some other strategies to actually do this kind of amine alkylation. And it turns out there's a bunch of different strategies to do this that don't involve alkyl halides, right? Because that's kind of the origin of the problem. If we just do an SN2, we really can't avoid this. So we need to use other kinds of intermediates that we can then convert into R groups. One way to get around the over-alkylation problem is to do a net alkylation. So here we would do multiple reactions where we start and where we end looks like a net alkylation. So if I don't know what all the reagents are or the synthetic intermediates that I'll have to make, but I know that if I go from here to here, I'm adding an alkyl group, right? So this would be like a CH2 with a benzene ring attached. So the idea here, one way we could do this is to amidate, so make an amide, and then reduce the amide. So that means that I need to add all of my carbons that I would want to introduce in the amidation step. So we know lots of ways to make amides. One way is to react things like acid chlorides with amines. So I could use this species. And I know it looks a little strange, but we can find this carbon here in the final products, right there. So I'm introducing all of my carbons, and I'm just introducing the carbon that's starred, which that would have been like an alkyl halide if we did SN2. I'm introducing it as a carbonyl instead. So I'm introducing the wrong oxidation level, but I'm building in a reduction step, so that should be okay. So we also know that these reactions require some kind of auxiliary base. So triethylamine or pyridine. So we'll use some good old triethylamine. And that means that we would first make an amide. So we can reliably add just one of these groups because when I make this product, this nitrogen, as we talked about in the first video, it's essentially no longer nucleophilic. I don't have to worry about this over-alkylation step or like an over-amidation. That's really not an issue in most situations. So here's my amidation. This is going to be selective for one new group added. So that's the crux of our over-alkylation problem, solving using an amide. But I need to get from the amide to the alkyl kind of product now. So that involves reduction of this carbon, which is at the +3 level. And I need to get down to the +1 level. So we know that amides are hard to reduce. They're not very electrophilic, and that means that really the only reagent that we know about as a class that will work for this is lithium aluminum hydride. So our kind of nuclear weapon reducing agents, and that also is going to need to work up. So here is my reduction step. And it looks to me like what we get overall is an alkylation. So we've gone from a primary amine to a secondary amine. You could do the same thing to go from a secondary to a tertiary amine. What would be different would be the structures of your starting material, the amide intermediate, and then also the product itself. But that's a pretty reliable strategy. So amidation reduction works pretty well. One thing that we need to watch out for here is we're using very powerful electrophiles. So in a situation where we've got multiple nucleophilic sites that could reasonably compete with an amine, this may not be a very good idea. And it's also the case that lithium aluminum hydride, remember, that reduces a lot of different things. And so if you have other reduction-sensitive functional groups, like maybe esters, for instance, you really wouldn't want to do this because those groups would also be reduced. So again, we're worried about this chemoselectivity idea, targeting the functional groups we want to change. Okay, so that's one of our ways to get around amine over-alkylation, is a net alkylation doing amidation reduction. There are also other ways to affect net amine alkylations that also circumvent the over-alkylation problem we saw when we tried to use SN2 reactions. So these are sometimes called reductive alkylations or reductive aminations that are used interchangeably, although reductive amination is, I think, the more common of these names, and it's certainly the one that I use. So this looks very similar to the amidation reduction strategy in that there'll be, well, reduction. But we don't use acid chlorides. We're actually going to use amines and ketones here. So let's look at an example. So we'll start with our same primary amine, and we're going to react this with one reagent that has all of the carbons I want to introduce to the nitrogen along with a reducing agent, and then we'll make some kind of a secondary amine. So in this example, let's look at making the same compound that we made using amidation and reduction. So that means I need to have this CH2 group, or at least a carbon here, and then a benzene ring attached. And so in the reductive amidation sequence, we'll use an aldehyde here. We'll see examples later where this could be a ketone. And then we also are going to add some kind of a reducing agent, but it's actually a pretty specific one. So we'll use sodium borohydride, but rather than 4 hydrogens, we're going to have 3 acetoxy groups. Okay, so NABHAOAC3, which, well, I can't even pronounce that phonetically. I'm not even going to try. So the idea is that, like, all of these groups, the H and then the 3 OAC groups, are all attached to the boron. So I'll draw the structure for this part. The sodium is just a spectator. So I've got a boron, a hydrogen. So that's an acetoxy group, OAC, and I'm going to have 3 of those. I'm going to abbreviate the other 2. So I don't have a lot of space. And we know that if I've got 4 bonds to boron, the boron's negatively charged. So this looks a lot like borohydride, but we've got these acetoxy groups instead. So this hydrogen here is going to react like a hydride. So we know that this is going to be able to reduce carbonyls and other things like carbonyls. Remember, this is back when we talked about sodium borohydride, lithium aluminum hydride. But this compound's less reactive or less reducing or less nucleophilic than BH4, NABH4. So less nucleophilic than NABH4. Okay, so this reaction works in a single step. So we'll literally mix the amine, the aldehyde, and the NABHOAC4, or OAC3, excuse me, in one vessel, just everything in together. So that's a lot more convenient than the amidation reduction procedure where I had to make the amide, probably purify it, and then actually do the reduction separately. It's also mild. We usually run these reactions at room temperature. This is not a compound we have to worry about catching on fire or anything like that. So in a lot of ways, this reductive amination is a much better strategy than amidation alkylation, although in some cases you can see it makes very similar or the same products. So the reductive amination works for both primary to secondary and secondary to tertiary alkylations of amines. So we could do our reductive amination here, check, and our reductive amination here, check, and we actually get very little or no over-alkylation. I mean, occasionally this happens, but generally this is a very highly selective kind of procedure. So generally, no over-alkylation. So the last thing I want to do is introduce another way of writing this, because it's kind of a mess with all those letters. People sometimes abbreviate this sodium triacetoxyborohydride. So sometimes we'll call this reagent STAB, which is kind of fun because, you know, when you run these reactions, and if you were a medicinal chemist like me, where I'm trying to make drugs to treat diseases, we make amines all the time, right? These are great for getting compounds to dissolve in blood, right? Amines, like we talked about in the first video, are easily tunable based on the structures, and so we really like them when we're trying to develop compounds to interact with a protein in a human body. So I did a lot of reductive aminations, when I was a professional medicinal chemist, and I would always sit there and add these reagents together, and I probably ran one of these reactions at least once a week. And I would just start adding this compound, and I'd be like, stab, 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 and all my colleagues thought I was crazy. So, you know, reductive amination, stab your amine. All right, so in the next section of this video, what we'll be looking at is actually the mechanism for this kind of reductive amination, because it actually helps us remember a lot of the things we've learned about carbonyls and what we're learning about amines. So let's take a look at how this reductive amination works. So we'll start with 3 reagents. The amine, we'll use the one from the previous example. An aldehyde or a ketone, we'll use the aldehyde from the previous example. And then the STAB reagent, which I'm going to depict this way, right? So the acetoxy groups are important for modulating the reactivity of the hydrogen. But what we're going to find in the mechanism is it's really the H and the B that matter here. So I'm going to try to make the structure a little simpler for us to draw. So we know from, well, I don't know, the entire semester that the carbonyl carbon here is going to be my electrophilic center. And now I've got 2 different nucleophiles, the amine and this, well, I guess it's the BH bond, the electrons that are within that bond. And because of the acetoxy groups, which are good inductive acceptors, we're actually going to make this hydrogen less nucleophilic, which we talked about in the last section of the video. And what that means is that the amine is going to be a much better nucleophile than our BH bond. So amine is our better nuke. And that allows us to make a prediction about what will happen first. The amine nitrogen will add to our carbonyl in the way that we've seen before. This is SLO7 that we're working on. So we'll have an intermediate that we would describe as tetrahedral. It would look like this. And the STAB is just watching. So I'm not going to draw the structure again. We're going to see a few steps where this is just chilling. So I don't want to redraw it every time. So this looks like an addition, and then we'll have a proton transfer. I'm hoping this mechanism is feeling kind of familiar at this point because it turns out you've seen it before. So I'm going to show this as an intramolecular proton transfer. Could be solvent assisted. So we get to here. This is our hemiamine now. And so one of the things that's kind of cool about STAB, we actually make it by mixing acetic acid, so ACOH, yeah, with borohydride. And so some of the hydrogens from borohydride essentially get protonated off, and we exchange for OAC, these OAC groups. That also means that there's usually a little bit of acetic acid around. So we've got a pH that might be 5 or something like that, kind of weakly acidic. And so what we can do is use kind of a hidden reagent. So H+, but I want to make sure we know where this is coming from. From trace acid in NABHOAC3 in our STAB reagent. Oops, parentheses in the wrong spot. Does that count as a misspelling? I put the parentheses in the wrong spot. So some people also add a few drops of acetic acid to the reaction, right? But usually the reagent has just a little bit in it. And so that allows us to protonate our oxygen. The oxygen's not the most basic site in the molecule. Typically you'll protonate the nitrogen, but that's reversible. And so eventually you end up making an intermediate that allows us to go forward in the mechanism. So we have our water which is still attached, so we've got a positively charged oxygen. Excellent leaving group now. And so we can essentially push that water molecule off. So this is reversible. So we get, I think I got enough space. Here, we call this an iminium ion, which means it's an imine or an imine, but it's positively charged because it's been protonated. So we've also got a water molecule. So I'm going to say minus water. So we get here, everything's reversible, but at this point we've got now a highly electrophilic carbon. Because of the positive charge on nitrogen. So this sounds a lot like protonating a carbonyl to make it a lot more electrophilic. You can protonate an imine to make it a lot more electrophilic. And now you've made something that's even more electrophilic than the carbonyl you started with, which is kind of cool. And here is where the stab actually gets involved. So whatever. Who cares about where the parentheses go? So now we can do our hydride addition. And this last step is irreversible. So basically we're in all these equilibria, every once in a while we get some iminium ion, and then stab like pounces and stabs it. Yes, that was cheesy, now I don't care. So that gives us our lone pair on nitrogen back. And just to be clear which H we added, right, it's that one that comes from stab. And then we had an H on this carbon the whole time from the aldehyde. So the one in black is from the aldehyde, the one in red is from the stab. So this is our mechanism for reductive amination using sodium triacetoxyborohydride or stab. You can see that it's an imine formation and then a reduction of the imine essentially. And actually before this reagent was invented, people just used borohydride for this. And you've seen that. Actually, in one of your homework assignments, you discovered this concept of reductive alkylation or reductive amidation, where you first made the imine, went for a coffee break or whatever, and then added the sodium borohydride. So the stab is nice just because you can dump everything together and just go home and then come back the next day and voila, you've added a single alkyl group. So of all of the strategies we've discussed here, SN2, amidation reduction, and then also reductive amination, reductive amination is by far the most powerful way to introduce selectively a single alkyl group to your amine. So in the next section of this video, we'll be looking at not how to alkylate amines, but a couple of strategies, and there are many, but we'll just talk about two, to actually make amines from some other functional group. So basically, where do these things come from in the first place? So up to this point, we've been assuming the existence of amines, but that's not really how this works. We need to make them from different kinds of functional groups. So there are lots of ways to do this. Given how popular amines are for a variety of applications and how common they are in biochemistry, chemists have spent a lot of time trying to figure out how we can introduce these groups. So let's look at just a couple of methods. We'll look at reductive methods first. So typically what we'll do is use nitrogen at a very high oxidation level, and then we'll try to reduce it back down to an amine. So one option is the reduction of nitro groups. So let's look at an example. So we'll look at nitrobenzene. This is a more popular strategy for making anilines than like regular amines, but it does work for regular amines also. So what we'll do is some kind of reduction. We'll talk about the reagents in just a second, where we end up making our NH2, and it looks to me like we'll make 2 molecules of water to account for both of these oxygens. All right, so we're reducing the nitrogen center quite a bit, actually. And we can do this in a variety of ways, right? So lithium aluminum hydride works, but again, like, probably the best way is to actually do a hydrogenation, which you learned about last semester. So this actually involves H2 and some kind of metal that's been finely divided on a charcoal support. So palladium on carbon is common, but you can use other metals as well. And this actually works really well, right? So you can usually just have a balloon, like a party balloon full of H2, right? Very like basically atmospheric pressure, and tiny amounts of the palladium, and this works usually what we say quantitatively, right? So the yield is excellent. You typically don't have to do any purification aside from filtering off the palladium and carbon. So really nice. So this works for, definitely it's one of the most common ways to make anilines. It also works for alkyl amines, so you would have like an alkyl nitro group instead. But it turns out alkyl nitro groups are kind of dangerous. They're often very explosive compounds. And so we have kind of other strategies in some cases to make those kinds of groups. So there's another reductive method as well. And so that would involve first alkylating alkyl halides with nitriles, or making nitriles, and then reducing the nitrile group. So this would be a net amine synthesis. So we're going to call it cyanation reduction. So this occurs in 2 steps. So we'll have some kind of an alkyl halide, and we'll react this with Cn minus as a nucleophile. So you could use NaCN or KCN for this, and that will make a new nitrile group. So we're cyanating this R group essentially. And then this nitrile can be reduced. To a primary amine specifically. So just to trace our carbons, this carbon here is this one here. And so this technique has some limitations. We're going to add both a nitrogen and a carbon, right? It's a little bit different than using the nitro groups. And our reduction chemistry is fairly aggressive, right? So typically the way that we would do this in a lab would be using lithium aluminum hydride. You can do hydrogenation methods like this, but the pressures are really high, and so are the temperatures in a lot of cases. So, on an industrial scale, that's fine, but in a lab, it's usually more convenient just to use lithium aluminum hydride. Okay, so these are a couple of more common reductive methods. You can use them interchangeably. There is definitely strategy involved with which one of those you pick, like if you're really making molecules for a living, but for us, like this is sufficient just to know, hey, they don't just come from nowhere. So then the last thing that we'll look at is called the Gabriel synthesis. So this is a little bit different, but it allows us to directly introduce a nitrogen onto an R group rather than adding both a nitrogen and a carbon. The so-called Gabriel synthesis allows us to take alkyl halides and convert them directly into amines. So we're going to fill in the space in between because this is actually a net reaction, so we're going to do multiple different steps to end up where we want to go. But what we can see is that this looks like a direct substitution of a halogen for NH2. So you might think, oh, well, I could just do this with like ammonia, NH3, and that would work really nicely. As we saw earlier in this video, alkylations like that lead to over-alkylation. So this isn't really going to work for us. So Gabriel's insight was rather to use essentially what we're going to call protected nitrogen. So we've talked about protected groups before. They mask reactivity. And the idea here was that we could take a group where there's a nitrogen, which will be nucleophilic, and then we'll put something on the nitrogen that blocks the other sites of reactivity. So given that a nitrogen could form 3 different bonds to R groups, like we saw at the beginning of the video, we need to block 2 of those positions of nitrogen in a way that will stay there until after I've made my new carbon-nitrogen bonds. And so the reagent that Gabriel came up with was this. So it's an anionic nitrogen. It's definitely a stabilized negative charge because of both of these carbonyls. And the idea here is that these carbonyls are going to make the nitrogen only able to add a single R group. So this compound has a name. This is called the phthalide anion. Right, so PHTH is very German. And this is going to do an SN2. So just like we did at the very beginning of the video, but now when I make the SN2 product, I have a species that looks like this. And our nitrogen lone pair is going to be distributed into this carbonyl and this one, right? So there's essentially an extreme amount of resonance stabilization of this lone pair. And that's going to make this nitrogen not particularly nucleophilic. So we actually can do a single reaction like this, right? This nitrogen in the product is no longer really functionally nucleophilic. Very poor nuke. So that gives us selectivity. So at this point, what we need to do is remove essentially, well, almost all of the structure. This is very wasteful, right? So we need to cleave away all of this stuff. This was all my protecting group. You can think about it like packaging, essentially, right? You know, like wrapping on the outside of the package, or it's kind of annoying, so it's more like that clamshell crap that you get in everything from Amazon, right? So it's like basically the nitrogen was packaged with all this other stuff to keep it, you know, sanitized for your protection. So how are we going to do this? Well, this looks like we've got CN bonds that we need to break. And we know that this carbonyl is on the carbon to that nitrogen. So it looks to me like we could hydrolyze these amines. And that's exactly what you do. So we'll do, you know, some kind of a hydroxide source. Sodium hydroxide, potassium hydroxide, it doesn't matter. And like water or ethanol, some kind of protic solvent. Typically, these compounds don't dissolve in water, right? So we would use things like ethanol instead, just for solubility, right? But it needs to be protic because the protons on the nitrogen come from the solvent. And the idea here is that we're just doing an amide hydrolysis. Right, which we talked about at length in SLO5. So the idea here is that this is essentially the base catalyzed version. Okay, so this is the Gabriel synthesis, right? It's another way to take alkyl halides and convert them into primary amines, right? So this only works for primary amines because of this packaging. So we've seen a few ways to do this, right? We could reduce nitro groups, we could cyanate and then reduce nitriles, or we could do the Gabriel synthesis to make amines from alkyl halides or nitros or alkyl halides, I guess. Okay, so in the last section of the video, we'll go back a little bit and look at a couple more examples of reductive amination just to see how we would think about product formation or predicting structures of reactants, things like that. So let's do a little bit of practice with reductive amination, since this is kind of the newest reaction for us. So you can see 3 different problems here. We'll work through them. I think it's going to be a good opportunity for you to try out what you've learned. And so what I'd like for you to do is actually pause your video and then work all 3 of these problems. So here you would predict the products. In the second reaction, you'd also predict the products. And in this final reaction, you would predict the reactants. So this would be 2 different compounds, a carbonyl-containing structure and an amine of some kind. So if you'd like, that's a great option, right, to make sure that you've internalized the lessons from the previous parts of the video, and then we'll reconvene. All right, let's look at these problems. So what I'm going to do is try to identify the kind of imine that I would expect to form, and then I can reduce that imine. So if you're working in pencil, strongly recommended, you can actually just draw the structure of the imine, and then all you need to do is erase a bond to end up with a reductive amination product, which is kind of convenient. So if I look at these 2 structures, I know the nitrogen is going to end up attached to our carbonyl carbon because the nitrogen is nucleophilic and the carbonyl carbon is electrophilic. So under these conditions, I would expect a loss of water or an amine condensation, and that means that I'll form initially a structure that looks like this. Okay, so in this structure, I'm going to lose both of the protons and the oxygen. That's the water going away. I want to make sure that I've got the right number of carbons on both of my groups, so I'm going to number and letter. So for the amines, I'll use numbering, where the nitrogen is attached to carbon 1, and then I'll work back down the chain from there. And then I'm going to find the nitrogen and work back down the chain. So 1, 2, 3, 4. So that looks good. I haven't lost any groups. They're all in the right pop, right in the spots. And then I'm going to do the same thing for the carbonyl-containing compound, but I'm going to use letters instead. So I'm going to make the carbonyl the lowest letter I can. So in this case, it would be B. 1, A, B, C. So like that. And then I'm going to find those same carbons in my imine. So A, B, C. Looks good. So the imine carbon should be where the carbonyl carbon was. Okay, so here's where the beauty of working in pencil is. So I know that this imine is going to form and there'll be a proton in the nitrogen. So I'm kind of thinking about this mechanistically, even though I'm not drawing all of the structures. And then I know that this imine gets reduced, which basically means I'm going to remove a pi bond. So all I have to do is that. And add an H on the nitrogen. There is also an implied H here, which you're welcome to draw. That's actually a good check on your work to make sure you've done that. And you can see that I've added two H's across where that double bond was, which is how we think about reduction chemistry. So that worked pretty well. Let's use the same approach here for this next problem. So here, numbering may not even be needed because I've got a ring and a substituent. So I can just make sure that these are para to each other. So I know that that benzene ring won't change, and I know that the halogen's not going to change either. So what's left for me to do is figure out which carbonyl my nitrogen is going to attach to. So I've got two possible electrophilic sites. And we know aldehydes are quite a bit more electrophilic than esters. This is also the 4, where this oxygen's a good resonance donor to this carbonyl specifically. And that means that I'm going to make my imine between this nitrogen and this carbon, where the aldehyde was. So again, I can simply draw my imine like so. So I want to check my work. There should be an ester carbon adjacent to the carbonyl carbon of the aldehyde, and that's where the imine will go. Imine carbon, ester attached, that looks good. And my nitrogen is still attached to the ring, that looks good. And so what's left for me to do now is reduce specifically the CN double bond, right? The ester is not going to react because we're using stab, which is a very mild reducing agent. Esters are not electrophilic enough to react with this compound. So I'll add my hydrogens, and I'm done. Not so bad. All right, so finally we'll go backwards. So we're going to look at the structure that was made from reductive amination, and I need to figure out what the feedstocks were. So this is harder, and a lot of times there's multiple correct answers because you can kind of choose which bonds you want to make. Like for instance, if we look back at this structure, I could have made this CN bond or this one. Either of those could have been done using reductive amination. Not so much the case here because I really couldn't have put a carbonyl on the carbon of the benzene ring. That wouldn't have made any sense. I'd go over the octet rule. So here we have to decide, and it turns out in this structure I chose this because there's only one correct answer. And if that's going to come down to where a carbonyl could have gone. So I'm going to think about either one of these CN bonds. I know that's what I'm making in the reductive amination, so I'm focusing on those two. So if I made this CN bond, right, then when I had an imine, it would have looked like that. See how I can just work backwards, add the double bond, and then basically running the whole reaction backwards. I'm saying, okay, well, first I'm going to do the backwards of the reduction. That gives me the double bond back. And then I would go backwards from the imine formation to get my carbonyl. So I notice here that I've got 5 bonds to carbon. I've gone over the octet rule. And that means that really it wasn't possible for me to make this particular carbon-nitrogen connection because I would never have been able to have a carbonyl here. It's not possible. On the other hand, if I look at this connection, right, so I'm going to take my double bond back out now. I know it can't be this one, so just to keep things a little clearer, I'm going to put my black line back in. I'm going to play the same game. So what if I had a double bond here? How would that look? Going to cut off pi. Like now I'm okay, right? Like I can play around with the number of hydrogens here. That's part of the reduction chemistry. And so this seems fine, right? Like if I had like a single hydrogen. Okay, so it looks like I've sketched out what would be an aldehyde if I took this back to the starting material. So it looks to me like we have an amine, looks like that, and an aldehyde, it looks like this. And I can check my work by using numbering and lettering. So I'm going to use numbers for the carbonyl this time. So carbonyl, carbon, 1, 2, 3. And then I've got methyls branching off of 3. That's far enough for me to go to make sure that I've done everything correctly. So it would be 1, 2, 3. Cool. So where I have an aldehyde, I would have an imine, and then that imine would be reduced to the desired product. For the amine, I'm just going to look to see that all of the same bonds are present and the CN bond is present, and I'm just putting H's on the end where I had the CN bond that I was trying to make. So reductive amination, very powerful. If we don't have any organized way to approach these problems, it can be kind of difficult because there's a lot of structural change going on, but I think this is a good place to actually use what you know about the mechanism in kind of a shortened way, right, where you can essentially make some predictions on the basis of that knowledge.